Hey everyone, and welcome to this explainer. Today, we're tackling the fundamental question at the absolute core of the whole artificial intelligence revolution. Seriously, how do these algorithms actually process, adapt, and, learn from data? We throw that word learning around a lot when we talk about AI, but behind the scenes, it's really just this fascinating structural process of mathematical optimization.
Okay, let's dive into this. It's incredibly easy to look at a highly advanced AI model today and just assume it's operating on some kind of digital magic, right? But at the end of the day, machine learning is really just advanced data processing. It's literally the science of designing methodologies to extract valuable, repeatable patterns from massive data sets.
I absolutely love starting with this classic definition from Tom Mitchell's 1997 textbook, mainly because it just strips away all that sci-fi mystique. Quote, "A model is said to learn from data if its performance on a given task improves after the data is taken into account." Unquote. That's it. Learning simply means an algorithm is automatically finding hidden patterns and mathematical structures in data to continuously optimize its own internal parameters. The whole goal, just to build a predictor that generalizes well to totally new, unseen data in the future. Part 1. Supervised Learning, the teacher. So to understand how this parameter optimization actually happens, let's look at the two primary pathways algorithms use, starting with our first pillar, the teacher. To make this super concrete, let's use a really didactic analogy. Imagine you want a model to recognize an apple. You sit down with it and you feed it thousands of photos, explicitly labeling every single one as apple. You're basically providing the exact answer key. But on the flip side, we have the explorer. Imagine handing the algorithm a giant chaotic basket of totally unknown random fruit and just telling it to sort them out autonomously based on their physical traits, without ever giving it a single name. Formalizing our teacher analogy just a bit, supervised learning is really all about predicting an outcome based on input measures, and it's guided by a known ground truth. You feed the model a massive data set of examples along with their corresponding labels. The algorithm makes a prediction, compares its answer to that ideal ground truth, and uses what's called a mathematical loss function to measure its error. It then adjusts its internal parameters to minimize that error over time. It's highly precise, but it strictly requires an environment where the correct answers are already known and provided upfront. Part 2. Unsupervised Learning, the explorer. But what happens when we don't have the answers? Well, here, the algorithm is left entirely to its own devices. So the crucial point is that unsupervised algorithms are operating without a safety net. There's no pre-existing outcome measure, there are zero ground truth labels to calculate a traditional loss function against. Instead, the model is tasked with discovering intrinsic patterns, latent factors, or natural groupings hidden deep inside raw data. Because it's not trying to predict a specific target, it essentially has to figure out what the important questions even are. And this brilliantly illustrates exactly what we mean. Starting with a totally raw cloud of unlabeled data points scattered in a two-dimensional space, an unsupervised clustering algorithm scans these points, calculates the distances and correlations between them, and organically groups them into three distinct natural clusters. No human ever told the machine what those groups represented, right? It just found the structure completely on its own. Taking this just a step deeper, there is a popular algorithm known as k-means clustering, and it basically works completely blind. The machine is given an objective, say, find 3 clusters, but it actually has to iterate through multiple random assignments to find the optimal grouping that separates the data best. It's exactly like our explorer sorting that giant basket of unknown fruit. The algorithm might organically realize, hey, one cluster is round and red, while another is long and yellow, perfectly separating the apples from the bananas without ever actually knowing the words apple or banana. Part 3. The semi-supervised gray area. Now, in the real world, generating high-quality labeled data for our teacher models is incredibly expensive and extremely time-consuming. You obviously can't just hand-label the entire internet, and this operational bottleneck is exactly what gives rise to the semi-supervised gray area. Here's how it works. First, you collect a massive, easily obtainable amount of raw, unlabeled data. Second, human experts hand-label just a tiny, initial seed subset of that data. Finally, the model relies on structural assumptions, essentially using those unsupervised grouping techniques we just talked about, to automatically propagate those seed labels out to the rest of the massive raw data set. It's this brilliant combination where a tiny amount of teacher guidance helps the explorer navigate a vast wilderness of data. Let's look at a really practical example from our sources. Take a Twitter profile for MIT's Computer Science and Artificial Intelligence Lab. In a semi-supervised model, A human might manually label just the hashtag AI as belonging to the category of computer science. The algorithm then clusters the text and notices, hey, hashtags like hashtag ML and hashtag big data frequently appear in the exact same profiles and contexts as hashtag AI. By leveraging that structural similarity, the model automatically labels those surrounding hashtags as computer science too. That literally saves thousands of hours of manual human annotation.
Part 4. Choosing the right approach.
Let's move to and see how this builds into the technology we use absolutely every single day. Bringing these abstract statistical concepts back to reality, how do data scientists actually choose which learning pathway to deploy? Well, supervised learning is used for precision tasks where we have crystal clear historical data. For instance, spam detection relies on thousands of emails previously marked as spam by human users. Stock price prediction trains on hard historical financial data to forecast the future. On the other hand, unsupervised learning really shines in exploratory and grouping tasks. For example, Netflix and Amazon use matrix completion and clustering to act as massive recommender systems. They're finding hidden genres or latent factors in user behavior to group similar shoppers and viewers together, and they do it without needing a rigid, predefined label for every single preference.
So what does this all mean for you? Well, it brings us to a pretty fascinating thought to leave you with today. As you navigate the internet right now, your clicks, your viewing times, and your browsing habits are largely just raw, unlabeled data. You aren't explicitly telling algorithms who you are. Yet constantly in the background, unsupervised learning models are calculating similarities, measuring distances, and clustering your behavior alongside millions of others. They are discovering hidden structures in your digital footprint that you might not even realize exist yourself. Crazy, right?
If you want to keep pulling back the curtain on how these algorithms actually work and continue exploring the fascinating architecture of artificial intelligence with us, please make sure to hit that subscribe button. We'll be doing plenty more data-driven, visual deep dives right here on this explainer. Thanks so much for joining me, and I'll see you in the next one.